In a previous video, we walked through how to use the chip spec to identify security issues in an image build. And in this video, we're going to look at how to actually fix those issues. So as a brief recap, chips or container hardening priorities is a set of security criteria that you can apply to container images. For example, it will check that there's a non-root user. And we also have an automated scorer that will attempt to grade images automatically. So what we're going to do today is look at the results for a fairly representative project. And we're going to see how we can improve them. Now the project's in Python, but pretty much all the work can be transferred to any sort of container image build process. Okay, let's jump straight to the terminal. So this is the project we're going to use. It has Dockerfile, it has some Python codes, so it is a working application this time. And this is the code, so all it is a simple Flask application that returns hello world. And we have the Dockerfile. Now I have already built and pushed this image, so to run it through the checker, all I need to do is run this code. So we're using the Dockerfile, we're using the scorer, and we're checking this image which I've called emote simple docker python chips. Okay, so that's run, and we've got these results. The major problems we're seeing are in minimalness, so it's quite a large image with the shell, package manager, debug tooling, and also in CVE. So there's quite a lot of CVEs in this image, and that's the first area we're going to tackle. There's also one here that we'll tackle at the same time, which is files with elevated privileges. So that's certain utilities that basically run with root privileges. So this is a Docker file. Here we see it's using Python Docker official image from the Docker Hub. And that's causing a lot of the issues here because that official image includes a bunch of build tooling. It includes things like make and GCC, and it also has a shell and a package manager and so on. So it's appropriate for building our image, but it's not so great when it comes to running our image where we don't need all that tooling, we just need enough to run Python. So what we're going to do is we're going to try and change this to a multi-stage build. At the same time, I'm also going to move to use Chainguard images because Chainguard, one, provide a minimal runtime image, but they also provide zero CVE images. So all the software is constantly updated in Chainguard images to make sure that it tries to remain CVE free. That's just about it. So this should give us a multi-stage build, and it should run as a non-root user. Let's try it. Let's just check it still runs. Okay, that looks good. I'm not going to bother pinging the endpoint. So we've got a multi-stage build. It builds, it works, and runs. And next step is to push it. And then we can run our checker on it again and see how much further we've got. Now this pull should be a little bit faster this time because the image is a lot smaller. And here you can see we're now passing all the minimalism criteria. We've still got an issue with unpinned references. We've still got an issue with not being signed. I'm going to come back to this point about pinned packages. And it also doesn't have an SBOM. But now we're going to check the CVE criteria. And if I scroll back up, those are good as well. So it's clear CVEs and now a minimal image. So we still got signing and pinning and SBOMs to look at. So let's make a start by looking at pinning. So the issue is that these images do not have a digest, right? So every time I pull python latest-dev, I can get a different version. And we really want to get the same version every time we pull it, just for reproducibility. And you can easily do that by adding a digest. Now, what's a digest? Well, it's a hash of the contents of the image, so you're guaranteed to get the same thing every time. What does it look like? Well, we actually saw it above, or in the Docker builds and so on. But what we're going to do is use Crane, so Crane's a simple container utility tool, and one of its features is digest. So I can type Crane digest, then the name of any image, and it will return the digest for that image, or the current digest for that image. So I'm going to ask for the current digest of the Chainguard Python latest dev image. And it's given me that. So I can now take this and we're going to put it in here. And the formatting is at, and then the big long SHA. So not very human readable, but great for reproducibility. And we also need the Python version, Python latest version. And that's there. Okay, so that's fixed the pinning issue for the images. Now, we actually passed the pinning issue for the packages because it came from file. And at the minute, the Discover program isn't clever enough to go and look in the requirements.txt file. But if we look at our requirements.txt, things aren't pinned. Now, there is a pip freeze command. So I can run pip freeze, and it will give me a list of all the dependencies of my application and their exact versions. So we can now replace our requirements.txt with that. And we have something much more reproducible. Now, I did recently find out you can pass a -- hash for your requirements.txt to specify an exact hash version of dependencies. But that's not supported by pip freeze at the minute. So you want to use that, you'll have to use pipend, or even better, move to a different tooling such as UV, which has better support for supply chain security. Okay, so that's handled minimalism, and we've handled CVEs, and we've handled pinning. The next two things were signing and SBOMs. So SBOM stands for Software Bill of Materials. And basically it provides an inventory of all the software inside an artifact, in our case our container. Now there are different ways to do this, there's a different tooling out there, and there's a bunch of nuance and writing on this topic, so you may well want to do your own research. But for the purposes of this video, we're going to use Sift. Now Sift is a pretty good solution, it comes from Anchor, totally recommend checking it out. So we can run Sift on our container image, and what it's going to do is parse the image, look at the file system, and tell us what's there. So it's found all the APKs and all the Python libraries there. So we've got things like Python, which we expect to be there, and we have things like our Flask library. So this looks about right to me. Now the next thing is we want to attach this SBOM in a standard format to our image. And you can do that with an OCI registry by using attestations. And Sift will use cosine to do this in a way that's always linked to this exact image with this exact hash. When we attest something, we do want to give it a digest so that we know exactly which image we're attesting. So I'm actually going to use Crane again to get the digest again. So I know this is the current digest from the registry. We could also go back and verify that this corresponds to the image that we built earlier. So now we're going to do Sift attest, and we want the SPDX format. If I don't specify SPDX, it will use the default Sift format, which isn't what we want. And we really want like a standard format that's understood by various other tooling. SPDX is quite voluminous, so if you look at it, it's going to be a very large file with a lot in it, and essentially all it's giving you is the same information as above. Now, like I said, this is using cosign, so it's going to want me to sign this attestation. And the way it's going to do that is by using this device flow. So basically, I'm going to copy this code out here. And you won't see this flow as it's in a different window. Basically, it's asking me for an OIDC credential, and it will use that in the signature flow. So basically, we have now an attestation that more or less says that this SBOM was created by somebody with access to my OIDC credential. Now, we could use this cosign command here to download that attestation, but like I said, it's a big SPDX document. I just care that it exists, and we'll use the score to check that in a minute. What we're going to move on to is the final thing I want to show you, and that's signing. Now, signing used to be a pain in the arse because you used to have to create keys and take care of them. Like you always had to make sure your private key never got compromised or lost, and it was a pain, honestly. So I'm really happy that cosign has been created, or SigStore project has been created, and it has a flow called keyless signing, and that's what we're going to do here. So I'm going to say cosign sign, and we're going to sign this same image. And it's going to enter me into a very similar flow as the one we just saw. So in the background, I'm doing this OIDC credential thing again. I'm actually using my GitHub credential. So basically what we're saying is this image was signed by somebody that had access to my GitHub credential at this exact point in time. And if you're interested in cosign, the SigStore project, please do go and look at the sigstore.dev site. Okay, so that's it done. That's one command, and we've signed this image. So I think that's about it. We're going to run the scorer again, and I'm hoping we get a clean bill of health. Okay, we've done it. We've got a clean bill of health, and I'm really happy with this. We did a few things there. We moved to a multi-stage build. We moved to Chainguard images. We added pinning. We added signing, and that's about it. Now, several of these steps you need to automate. So you need to be doing the cosign in your CI/CD workflow, and you also need some sort of flow for pinning and updating of digests. I would like to do another video where we walk through doing this all in GitHub Action, so all your signing and your pinning happens automatically. But hopefully I've shown you how you can fairly easily take your image score from an okay score to an excellent score with a few steps. So I really hope some of you follow the advice on this and do some of these things. As ever, please reach out if you have any questions.